Okay. Sampling distributions of sample means. We've been studying sample proportions. Let's do the same for sample means. Central limit theorem states that sampling is like a random variable, a random event. Sometimes you get more than you would have thought. Sometimes you get less than you would have thought. But given a large enough sample size, that distribution becomes normal for sample proportions and sample means. Let's for sure make first that a normal distribution is a reasonable assumption by checking some basic conditions. Just like sample proportions, I have to collect my sample randomly. My sample needs to be less than 10% of the overall population so that each sample is independent. This third one is a little bit different than what it was for sample proportions. For the sampling mean distribution, I have to select from either a population that is normal to start with or have a sample size large enough so that the central limit theorem applies and we can assume a normal distribution. Kind of common convention is that a sample size of greater than 30 will make the sampling distribution normal if it wasn't already to start with. Either we're sampling our population from a population that's normal, or we're sampling from a population enough times in order to make it normal. Or use the magic number, common convention. If those three conditions are satisfied, assuming a normal distribution should be pretty reasonable. Random sample, less than 10% of the population, so each sample is independent. And to be sure that the central limit theorem applies, either the population should be normal to start with, or we sample enough times to make it normal by central limit theorem. Over here is the center and spread of our sampling distribution. When I take a sample, I should expect that that sample mean is the same as the population mean. So the average of x bar, the sample mean, should be the same thing as mu, the population mean. So review on notation. X bar is the notation for sample mean. Mu is the notation for population. When I take a sample from some population, I would expect on average my sample mean to be the same as my population. But there's some variability. Sometimes I get more, sometimes I get less. Sampling is like a random event. That variability is given by the standard deviation of x bar. The standard deviation of our sample is the standard deviation of the population divided by the square root of n, our sample size. This would be the population standard deviation. Lowercase sigma is notation for population standard deviation. Since we're assuming a normal distribution, a z-score could be found by taking the difference between the sample mean and population mean. How much more or less did your sample mean differ from what you should have gotten? X bar minus mu divided by that standard deviation. Take the difference in your sample mean and your population mean to tell you how much more or less did you get from what you should have gotten. That difference divided by the standard deviation should give you your z-score. So overall, x bar minus mu divided by this same standard deviation value from above, sigma over the square root of that. Let's use z-scores for some sampling mean distributions on these two examples. Okay. first one up here. The weight of potato chips in order to be 10 ounces. So when you buy the bag of chips from the gas station, it says on the packaging on the label it's 10 ounces. There's 10 ounces of chips in the bag. The amount that the machine places in each bag is normally distributed with an average of 10.2 ounces and standard deviation of 0.12 ounces. So at the potato chip factory, the machine that puts the chips in the bag puts an average of 10.2 ounces in every single bag, with a standard deviation of 0.12 ounces. Why would they put more than advertised in the bag? Why would they actually put 10.2 ounces in the bag as opposed to 10 ounces? Why are they giving them more than they're supposed to?
End up with less.
What's that?
They could end up with less.
Right. The machine isn't perfect. There's some variability. We're going to differ from that 10.2 ounce packaging average by about 0.12 ounces. It would be pretty bad if somebody got less than 10 ounces and I'm ripping them off, right? I'd rather give them more than they're supposed to by a little bit than less than they're supposed to get. Does that make sense? So what is the chance that the average weight of a 3-bag package of chips is less than advertised? What's the chance that when somebody buys a 3-bag package of chips, the average weight of those package of chips is less than it's supposed to be? They're getting ripped off. So let's start figuring everything out. We've got a couple of different averages up on the board. Let's first identify what the sample mean is and the population mean is. The amount that the packaging machine places in each bag is normally distributed with an average of 10.2 ounces and standard deviation of 0.12 ounces. Is this value, is that the population mean or the sample mean? Population, because isn't that every bag that this company's making? All the bags, our sample mean, our population mean is 10.2 ounces. So mu is 10.2 ounces. Of course, that's got some variability. Sometimes they're going to hit their target, sometimes they're not. So the standard deviation at average, sigma, is 0.12. When I pick 3 random bags, what's my sample size? 3. What's the chance that of that sample, they're getting less than they're supposed to? What are they supposed to get? 10. So our sample mean is 10 ounces X bar. Does that make sense so far? Overall, the bags are filled up with 10.2 ounces on average. What's the chance that my 3 bags got less than they're supposed to, 10 ounces? All right, let's first check a couple conditions to make sure we can use a normal distribution here. Are these 3 bags in the sample selected randomly? Sure thing. Is 3 bags less than 10% of all the bags produced by this company? I would certainly hope so. Now this last condition is a little bit different. Sample size is kind of a big deal when I'm talking about sample means. Either the population has to be normal to start with, or to make sure that central limit theorem takes over, the sample size has to be large enough. 30 is the common number there to use. Right now, my sample size isn't large enough. Is that a problem? I've only got 3. It needs to be 30 to make sure that the population doesn't matter. But what else was given to us? The bags are normally distributed when they're being packaged. The amount being placed into the bags is normally distributed initially to begin with. So the population is normal to start with. It doesn't matter I'm only picking 3 bags. It's normal anyway. Who cares if I'm picking only 3 bags? So population is normal. I can choose any number of bags. Doesn't matter if it's less than 30. My z-score formula to find its probability is x bar minus mu divided by sigma over root n. How much above or below we're supposed to are these consumers getting? Supposed to get 10.2 ounces. I want them to have 10 ounces. So 10 minus 10.2 divided by 0.12 over root 3. What's the chance that these 3 bags are getting 0.2 ounces less than they should when I'm sampling 3 bags? I get a z-score from the computer there of negative 2.89. Why is it negative?
Because 10 minus 10.2 is negative.
So they're getting less than they're supposed to. I'm different from what I'm different than what it's supposed to be by 10.2 ounces less. Negative 2.8. Z-table time. Am I looking for the right part of the tail or the left part of the tail? Which part of the distribution am I looking for? Let's say left here.
Because
Less than average. So look up the proportion or probability of a z-score less than or equal to negative 2.89. On your z-table, that's going to be 0.2%. Pretty rare. Because they have a pretty accurate machine. The standard deviation is only 0.12 ounces. So they hit their target weight more often than not for the bags of chips. Another one. Mosquitoes have short lifespans. Their lifespans are strongly skewed to the right with an average of 8 days and a standard deviation of 5 days. Biologists are going to take a random sample of 32 mosquitoes to study over the course of their lifespan. What's the chance that the average lifespan of that mosquito sample exceeds 10 days? We're going to take a look at some mosquitoes. Mosquitoes have a strongly skewed to the right lifespan with an average of 8 days and a standard deviation of 5. So biologists are going to take a random sample of 32 different mosquitoes to study what's the chance that they're going to be around for 10 days or more. There's lots of different averages up on there for that question. Let's first make sure I know what X bar and mu both are. This 8-day average, is that the sample mean or the population mean? Population, why? Is that all mosquitoes or the mosquitoes they took a sample of? All of them, right? Population is everything. So overall, mosquitoes should last 8 days. So there's mu. Standard deviation of 5 days. That would be sigma. We're going to take a random sample of 32 mosquitoes. Their sample size n. What's the chance that the average lifespan of the sample exceeds 10 days? This 10-day average, is that the sample mean of the population? Of the mosquitoes that they've collected, what's the chance that they stick around for 10 days or more? right, so before I can conduct my inference, let's make sure that the conditions for normal distribution are met. Mosquito sample was done randomly. Cool. 32 mosquitoes is less than 10% of all mosquitoes that are out there. Not much difficulty assuming that. Last condition says this. Either the population is normal or the sample size is big enough so that central limit theorem takes over. It's more than 30, right? Even though the distribution is not normally distributed because it says skewed to the right here. We're taking 32 mosquitoes, so central limit theorem takes over and makes the distribution normal anyway. So our sample size of n is greater than 30. Alright, so z equals x bar minus mu divided by sigma over root n for the standard deviation. So z equals 10 minus 8 divided by 5 over radical 32. I get a positive z-score, 2.26. Why is this positive? I know the last one was negative.
That's because sample is more.
They're living longer. They were supposed to. Supposed to live 8 days. I want to see if they're going to live 10 days.
We want to see them live like
So
days.
longer. I'm also going to try and find the probability that my z-score is greater than 2.26 because they're going to exceed that 10-day average. So rather than the left tail from our z table, we're going to look up the right tail. 2.26 and above is where? 9881. I want the right tail of that distribution, so 1 minus 0.9881.
Oh, 1, 1.
About 1.2%. Just about the time we had left there. All right, let's do one more before you go. Grab your practice. I'll have you do the next question